These are the notes for section 3.1, graphing polynomial functions. And what we're going to be doing in this section is kind of graphs that would be similar to those that we did in the calculator in the last chapter, but the difference is we're not using the calculator. So to accomplish that, you're going to need a pretty good list of stuff to get a decent graph, because we're going to really do a fairly accurate graph without using our calculator. Now, before we start talking about the graphs, the first thing is kind of define a polynomial function a little bit. And some simple ideas going on here, like a polynomial is basically a smooth curve. That means no breaks, no sharp corners. It might be good to think about the kind of graphs that are not polynomials. For example, absolute value. Because that V shape has a sharp turn, or what we call a corner. Graphs that are piecewise, where you've got kind of that visual break somewhere where you go from one graph to the other graph. So, maybe you've got something like this, and all of a sudden you've got something like that. Okay. Piecewise graphs. Other graphs that would be good examples of not polynomial would be those graphs that are like rational functions, where you've got asymptotes going on because they have breaks. So those would be examples of not. Just about anything else, a nice, smooth, continuous curve, going to be a polynomial. And a good example to get us started is a quadratic. So we'll start with that and look at some of the basic functions also. Okay. So here's a quick snapshot of the basics. And remember from chapter 2, I call these standard functions. And we're not going to do much at all with lines and probably hardly anything with parabolas. But it's good to know how functions that have exponents 2 and larger behave. And so we'll start with end behavior. End behavior is one piece of the puzzle. There's a lot of things going on that we're going to talk about for graphing. But end behavior talks about what will eventually happen. So we're talking about the ends. Those are the ends. Or in third power, those are the ends. So what eventually happens? Because in the middle, there can be all kinds of changes in direction and different things going on. Now, what's kind of good to know right away is that even power graphs behave the same way, and odd power graphs behave the same way. If you think about a parabola and it being positive x squared, well, the idea is kind of simple as far as behavior goes, because in like algebra 2, you would have said a parabola that opens up. But when you're saying opens up, you're actually saying that both sides rise, so they have the same behavior. If I make this negative, and I go negative x squared, well, now that parabola is going to open down. And its behavior is going to be that both sides are going to fall. And if you look at x to the third and x to the fifth, and all odd power graphs do this, they go in opposite directions. So while one side will rise, the other side will fall. And imagine you make it negative. Now, what does negative really do? What negative really does here is it causes a reflection. Reflection over the x-axis. So by making it negative, you're going to cause the behavior to change. So the positive or negative is going to be the first thing that we'll kind of talk about with behavior. And then the actual exponent itself will help us figure out what the other part of the graph is going to do. There are a set of rules for behavior, but I think you guys really should not operate on a set of memorized rules. You should just operate on the fact that you know what parabolas do, and you should know what third power graphs do. And then all other graphs that are either even or odd will be similar to those two. And so we'll have a set of rules, but I think those set of rules are more like a backup. You should just really know what the graphs do. So, behavior. And the other thing to think about too when you talk about behavior graphs, if you go even odd, if you want to stay in that little vein for a second, think about last chapter, even odd functions. Even functions have symmetry over the y-axis, which means that would cause them to look the same on each side, which matches up with the idea of behavior being the same on each side. And if you look at odd functions have rotational symmetry, which means if you rotate that 180 degrees around the origin, you get the other half. Or rotational symmetry causes graphs to do the opposite on both sides. So the idea of even odd as a function of symmetry concept from chapter 2 matches up with even odd as an end behavior concept in chapter 3. Okay, let's build up the idea of end behavior a little bit more, and then we'll start talking about the other stuff in the list. And we're going to make this list a pretty extensive list of stuff that we'll use to draw some graphs, and then once we get that list developed, we'll go ahead and do some graphing. So it's always good to start with just like x squared, because parabola is something you're used to, you're familiar with the graph. Talking about behavior, when I talk about behavior, what I usually do is I discuss it as rise and fall on the two sides. You can visually tell it's pretty clear that the graph rises on both sides. We're going to use some symbols now to kind of help us get into the groove with the rules for end behavior. The symbol here is what's called the lead coefficient, so a subscript n. lead coefficient. N is what we call the degree. And degree, so we're clear on what degree is the largest exponent. So x squared would have a lead coefficient of positive 1, and it would have a degree, that's even. Now, we're most concerned about lead coefficient, is it positive or negative, because that actually tells us the idea of kind of like opens up, opens down. And degree even or odd, because all evens behave a certain way and all odds behave a certain way. And so that way we can discuss the rules in terms of lead coefficient and degree. So if I'm describing the end behavior of this parabola, it rises on the right side, it rises on the left side. And the reason it does is because the lead coefficient is positive and the degree is even, which means even graphs do the same thing on both sides. Now, to kind of summarize the rules a little bit, here's the rules. So there's a function up top, and just to kind of practice identifying some stuff quick, make sure we know where things are at. Lead coefficient and degree are actually in the same term. So when you find the largest exponent, you've also found the lead coefficient. The lead coefficient is 4. And the degree,
voting, could you call and let us know where you're at? 58015, please.
sorry for that interruption announcement, that happens, I guess, right? So, and the degree is 3. But really what we're actually concerned with is the lead coefficient being positive and the degree being odd. Now, all odd degrees, all odd exponents behave the same way. They will do the opposite on either side of the graph. And the positive idea is the rise on the right, the odd, the opposite on the left. You know, the other thing about behavior is when I see a graph that's positive and odd, I might just think of this as my guideline without even a set of rules. That's generally what a third power looks like, a positive third power looks like. Now, if you want to focus on the rules for a second, what the rules say is if the lead coefficient is positive, you will rise on the right side. If the lead coefficient is negative, you will fall on the right side. So lead coefficient is right side behavior. Degree is left side behavior. And so the concept is if it's even, it should do the same, which you really already know. And if it's odd, it should do the opposite, and that's left side. So there is a set of rules, and those rules are fine, and you can learn them and memorize them if you like, but really if you just think about what you already know or should know, you don't have to have a set of rules to figure out behavior.
Good afternoon, Curry teachers. Could you please come to the lounge and vote for our EPEA?
All right, sorry for the announcement interruptions. We'll just keep plugging away here. So at this point, let's look at some visual ideas and just say, can you identify the behavior based on what you see? And then we'll actually flip it around and say, let's look at the functions, and again, one more time, practice behavior. So based on what you're seeing, and I think when I look at these, the first thing I would do is, do I have a degree that's even or odd? Now, right away, I can tell you that they're both odd degrees. Because they're doing the opposite things on the two sides, left and right. So they're definitely odd. Now, as far as me figuring out what's the lead coefficient is right side behavior. So when I see this rising, I know that means I've got to have a positive lead coefficient. Positive is like saying up. Positive is rise. On the other hand, if you look at the right side over here, it's a fall. So I mean that must be a negative lead coefficient, because negative is to fall on the right side. Pretty easy to figure out the rules. Now, both of these, again, when I see these two, my first thought right away is the degrees have to be even because they're doing the same thing, on each side. Same thing on both sides, rise on both sides or fall on both sides, automatic even. All evens behave like parabolas, okay? And that's just a matter of what do they do? Well, both sides rise, you gotta have a positive lead coefficient. Both sides fall, you gotta have a negative. Now really, it's right side behavior. And it's right side behavior. But I already know that even powers do the same thing, okay? So there's just a quick visual idea. Well, I'll kind of look at it and tell you what the behavior is. Now, the other side, the flip side, is to look at a function. And you can cruise through these in just a matter of seconds on each one. List it out real quick. And probably when you guys are doing problems like this on a quiz or a test, you may not actually list it out on paper unless you're asked to, like write down the lead coefficient, write down the degree. But that's what you got to focus on just to get your thoughts organized. So I'm going to run through them kind of quick. They don't take very long. And when I do lead coefficient, I think positive or negative. When I do degree, I think even or odd. then I'll use up down arrows to describe the actual behavior. So positive is rise on the right, odd is the opposite, fall on the left. So again, visually what I'm thinking about is a graph that's kind of like that. Okay. On this one, it is negative and odd. Negative means falls to the right, odd does the opposite, rises on the left. So that'd be a graph that's doing something like that. So again, you can clip through behavior pretty quick, pretty simple. Lead coefficient positive and even. That's up on both sides. Lead coefficient negative and even. Lead coefficient negative, degree even, I should say. That's down on both sides. Because again, what I'm visualizing is something that's like this or something that's like this. All even power graphs behave like parabolas. Okay, so end behavior, although we spend quite a bit of time here talking about it, really is just one piece, and kind of a smaller piece of the overall picture, but it's helpful as a good cross-check when you're done. And you'll see that later on a little bit when we do the graphs. Okay, let's build up some more of the list. So other things we need to know are what are the zeros of the function. So find all zeros. Now, we have already talked about zeros in the last chapter, probably in the review chapter, but we didn't call them zeros. Depending on what we were doing, we were factoring, we were finding intercepts, maybe we were solving way back in the review chapter. And they're all interchangeable concepts. But it's important now that we think about how we write them. So we want to write them correctly. So we do need to distinguish the difference in the way you write it. So I'm going to write down a factor to start, and we'll build off a factor. So there's a factor. Now, if I said find its solution, set it equal to 0 and solve it. Write that thing as an x-intercept. Cool. You start to see the visual difference. Now, what does it look like as a 0? So it's going to be important that you think about the difference in the way you write things now. So intercept as a coordinate, solution as x equals, factor as parentheses x minus or x plus. 0 is the number by itself. And it will be a difference in the way you write things, and we're going to expect you to do it a certain way. Okay, so I just wanted to kind of make that point quick. And then another piece of our puzzle actually is extrema. Now, we've talked about extrema already. We did local max and min in chapter 2. And the idea there was a change in direction. It's the same idea here. It's called extrema. Why they changed, I'm not really sure, actually, to tell you the truth. I think it's just maybe talking about the extremes of the graph, right? But it's simply max and min. And really, I think of it more as change in direction. And what we're concerned about is how many times the graph changes a direction. And that's going to be related to the degree. So whatever the degree is, so if we got quadratic, for example, degree is 2, the extrema should be 1 less than that. And if you think about this graph, changing direction really means a change from increase to decrease. Thinking about stuff in last chapter. And so we're talking about a decrease here. Then change in direction is a change to an increase. So extrema is a change in direction, and it will be at most 1 less than whatever the degree is. And that's like a kind of an expectation sort of thing. When you're graphing, then I'm expecting, before I start drawing, that I should have this many changes. And if it doesn't happen, or it doesn't match up with my coordinates, then I think maybe I got an error somewhere. So again, just one piece of the puzzle to help us out in the big picture. Here is the big picture. Now, there's one thing we haven't discussed yet, which is number 4. But the list of stuff here is you're going to factor the original function and find its zeros. So we're going to call them zeros now, right? So factor it, find its zeros. Those zeros become the x-intercepts. We'll do y-intercept like we've always done. We'll do end behavior. What are the rules? You know, what does it do on the left and the right sides of the graph? And every graph has a visual left or right. They may not be symmetrical, but you can take just about any graph, kind of cut it right down the middle, and you can definitely see a left and a right-hand side. Number 4, multiplicity of zeros, we'll talk about in the next video, because I'm going to run out of time on this one in a second. The number of possible extrema, so how many changes in direction, and then sketch the graph. Also, an extra step that we may or may not have to do, which I'll discuss in the graphs in a minute, is figure out if we need some additional points. So in other words, maybe the x and y intercepts aren't enough to help us draw the graph accurately, and we definitely want to try to draw it as accurate as we can. Okay, we'll pick it up here in the next video.